All right, welcome back to the Kitchen Research Group. Today I'm going to tell you about a recent collaborative paper on generalization of graph-based active learning relaxation strategies across materials, also known to us as Fine-Tuna 2. We wrote a paper about Fine-Tuna that is an idea where you take a machine learned potential to accelerate geometry optimization, and in this work, the machine learned potential is a graph-based neural net, and we look at materials that are outside that training domain. So these are the authors that collaborated on this work, and it is published down here. You can find a link in the video description. So in a nutshell, we do geometry optimization as part of DFT, where you take an initial guess for the geometry of an adsorbate or a molecule, you calculate the forces, and then move the atoms so the forces go down to zero, and we call this the ground state or lowest energy geometry. And each step requires a density functional theory calculation, so this is a fairly expensive part of doing DFT. And the algorithm that I described only requires that you have reasonable forces to move the atoms. And if you had a way to get cheap forces, then we might be able to speed this step up and just have a few or even zero DFT calculations would be ideal. Now, the Open Catalyst project provides pre-trained machine learned potentials that are based on graph neural networks that provide cheap forces. So for a typical system, it is less than a second for us to calculate forces with the machine learned potential. And so it's a very appealing idea to use the surrogate models, the graph neural networks, to get the forces instead of DFT. And it's important to note that these pre-trained models were trained on DFT, trained on very large data sets. So our first work focused on showing that this works for materials that the models were trained for. And in this work, we look at what happens when you use materials outside that domain. So the OC20 dataset was trained on lots of metallic slabs, intermetallic slabs, some sulfides and nitrides and halide materials, and fairly small adsorbates, lots of C1 adsorbates containing carbon, hydrogen, oxygen, and nitrogen. So we wanted to look at a series of increasingly out-of-domain materials. So we looked at some larger adsorbates in this work. And so if we have a C2 or C3 adsorbate, that's 2 or 3 carbons, those are not in the original training set, and you might wonder, well, how well does our model work? And we also looked at oxides, and these get outside of the training set. They're not included in the OC20 data set. And zeolites are an open porous material that is largely based on silicon oxide-like materials. So those were not in there at all. And so we wanted to explore how well this works. And in a nutshell, I'll tell you, with fine-tuning, that is, we take our pre-trained model and fine-tune it on the relaxations, we're able to reduce the number of DFT calls a lot. All right, so the workflow setup test system that we have, we start with an initial structure. We looked at 27 alcohol to ketone systems. These are in some sense close to the data set because it's the same materials, just bigger adsorbates. We looked at a series of oxide systems. These are different materials. And then we looked at these 81 different 3D structures, the zeolites. We also looked at 3 different functionals. So OC20 was trained with the RBPE functional, but we used a Beef van der Waal functional for the alcohol system, PBE for the oxide system, and RPBE for the zeolite systems. So different functionals and different materials and different adsorbates. There's a variety of kind of query systems you can use. We typically start with a initial structure, make some predictions from the MLP. We can either query DFT at the initial point or after case steps, or anytime we get a high force or error. And we looked at all of those. I'm not going to get into the details of each particular one. They're all in the paper. And then there's this cycle here that you make a prediction, do a query, decide if we're going to fine tune, or if it's optimized, we do a single point, make sure it's converged, and that gives us the final result. All right, the overall results are kind of summarized in this graph. There's a lot of information here, so let's take it one step at a time. If we look at the top graph, 100%, this line here is how many steps of DFT are required if you just use DFT. So anything below this line is accelerated, and anything above this line is actually more expensive. So what you can see looking across this, the alcohols, the oxides, the 3D structures, is that for most of these systems, the vast majority of them, we get acceleration. That means we need less DFT to get to a low energy solution than we needed before. And for a few of them, you see that it takes more DFT. And these are like the C6 is the farthest out of domain, and these oxides are also out of domain. And then looking at some of these, we also get some situations where they just don't converge. I'll get back to that in a little bit. So for the most part, you see across the board, we get a acceleration, less DFT required by taking this approach. There's also a couple of interesting things in the bottom graph. So the bottom graph is the relative difference from DFT. So for most of these, you see there's hardly a difference from DFT. That means we get essentially the same geometry from the MLP fine-tuner approach as we get for DFT. But for a few cases, you see that we actually find more stable geometries. So the energy is lower. And that's not a super big surprise. The geometry optimization relies on a local optimizer, and if you take a slightly different path, it is possible to find another local minimum. And they're not huge, 0.02 EV per atom is not a very large difference, and occasionally we find some that are less stable than more. So overall interesting that most of the time you get basically the same result, but you get it faster. There are a couple things that we learned that make fine-tuner work poorly. I'll talk about two of them here. One is the MLPs do not have any sense of spin or magnetism. And when you switch spin states, you can get changes in forces that lead to poor results. And so that's kind of shown here. We have two different approaches if we use different models that are trained on different data sets. Then you can get differences of, say, three Bohr magnetons. And this tends to lead to difficulty in converging because the MLP forces are not consistent with the DFT forces, and you can run into some trouble there. It is an open problem for how to incorporate magnetism in these models, and there's not a good solution coming anytime soon, I think. We've done some work in the past modeling magmoms and figuring out how to incorporate magmoms as inputs to the model so you can differentiate between them is still a challenge. The other problem we found is when your initial forces are very high, so 5 EV per angstrom. This is very high. You can see these X's over here. Lots of times when you start out and get a force like that, that is probably an indication you are far from training data, because these are extremely high forces. So whenever you get a force this high, probably there's two things that happen. One is you're probably getting out of domain, far from the equilibrium data and relaxation data that it's trained on. The other problem is that this leads to poor optimizer behavior because large forces tend to make big steps for atoms to move, and then the optimizers are not always even stable under these conditions, and that can lead to calculations simply not converging. So when you find yourself in this place, you should probably stop and try to figure out how to get a better initial guess that's closer to the answer you want. All right, so in summary, fine-tuner with MLPs is still very valuable. It's still good for using in systems that are considered out of domain. As you get more and more out of domain, fine-tuning is more and more required because the models simply aren't reasonable and aren't giving good forces if you get very far from things that it's seen. Some things like it's easy to use fine tuna. You can take the RPBE trained potentials and use it for other functionals. We've seen PBE, beef work fine, and that's mostly because those functionals don't make huge changes in forces. They of course they change the energy all over the place, but the derivatives are much less sensitive to that, and so especially with fine tuning, you can use a PBE or RPBE potential and fine tune it on whatever expensive DFT data you want. That seems pretty reasonable. But adding things like spin polarization is likely to cause problems because the forces are not insensitive to that, and that can lead to issues if you're trying to do that. So overall, fine tuna results in pretty substantial DFT reduction. We saw anywhere from 40 to 80% reduction, and so it seems like a pretty reasonable thing to continue trying to work out ways to smoothly integrate this into geometry optimization calculations. So thanks for paying attention, and stay tuned for more work in the future.